The old and the new. Artificial neural networks are powerful, but they have issues. And deep learning is going to address some of these issues, often by combining the new artificial neural networks with 300 plus years of applied math. So the course thus far, we've looked at pre-processing and model building, focusing on supervised learning, where the goal is a model of the form y equals f of x. X is in some vector space with some weights w. And this vector space is a feature space. It's usually been Rn, but we've seen a few instances where it's not. And going forward, our feature space will typically be a tensor space. For example, grayscale images are actually tensors. Color images are also tensors. And that means we get huge numbers of weights, many more than we get when we're just simply working with column vectors. The goal of pre-processing, if you remember, is to convert raw data into a vector space representation with features x. We've also seen algorithms as models of this form, supervised learning. And the function f can be and often has been defined by an algorithm. K nearest neighbors, decision trees, ensembles, boosting, bagging, stacking, which gave us random forests, the extras trees, gradient regressor. Now, a classifier, which we've also spent a lot of time with, is actually itself a function where the response is a probability distribution. So this is when we have r possible outcomes in some probability space. Maximum entropy, or minimum Kullback-Leibler divergence, is the kind of models that we've been looking at, subject to constraints, but otherwise we don't have to specify what they look like. And the Gibbs form played a central role. Deep learning is also models as algorithms, and in fact, it includes nearly all of the course we've seen so far as a special case. We also looked at kernel methods. So the curse of dimensionality is that high dimensional data points tend to be far apart and mostly uncorrelated. Low dimensional representations are crucial. So we do things like principal components analysis and non-negative matrix factorization. But there's also a blessing of dimensionality, which is that complex topologies are often simplified by mapping to higher dimensions. And if we have dimension n data that's embedded in dimension d space, then n small means that as a submanifold or a subspace of the very large dimensional space, it's still low dimensional. But in the very large space, we have the freedom to simplify. And in multi-layer artificial neural networks, interconnected networks of artificial sum and fire neurons that look like this. We tend to think of the inputs to a neuron as being a vector x, and then we feed forward, calculate z, which is actually a matrix multiplication, matrix algebra, and then activation on that matrix product. And we arrange these into layers. The result is a universal approximator of the true model that produces whatever data set or phenomenon we're looking at. Now, learning is via backpropagation, which is just the chain rule from calculus. And the learning goal is we're trying to move to where the derivatives of some expected loss are equal to zero, or get as close as we can. But there's an issue called the vanishing gradient. You see, if our only goal is to hope that the derivative goes to zero, then that can happen asymptotically. The derivative can go to zero just because we have these horizontal asymptotes, not because there's something we've learned from the data. So we've got the good and the bad for neural networks. The good, they're your universal classifiers. The bad, overfitting is a big issue. The good, energy decreases and artificial neural networks tend to store information at minima. The bad, there may be local minima. There may be spurious states that we don't want to learn. The good, backpropagation. The bad, the vanishing gradient. And what's really ugly is that neural networks require random interface for the weights. They don't always work, and they tend to have huge numbers of parameters. So again, we've got this multi-layer neural network, and notice that I'm denoting now my weights by Ki and J, where K is the layer, the kth layer. And so that means that my neural network is actually a composition of all these functions. In other words, if I define f sub j of x to be sigma of w sub j of x, then I actually have this composition of all these functions f. Now, you can show that for universal approximation, only the last layer must be a neural layer. The prior layers can implement classical mappings and transformations. In other words, we can think of these as ordinary functions with a forward and a backward direction. So what does that give us? Well, it gives us deep learning, universal approximators that learn representations. As we'll see, very often we'll have a set of layers that learns a representation followed by a neural network universal approximation. In other words, deep learning is neural networks with representation learning. Here, if you remember, here is Polya's method for solving problems in the data sciences. And deep learning incorporates both the computation and the representation aspects of Polya's method. So a layer in a deep neural network is a function with weights w modified by backpropagation based on a loss function. We have weights for our layer, and we have a feed forward, and then we backpropagate to modify the weights by looking at the errors. A deep learning model has many layers. It's essentially compositions that alternate between linear transformations, Wx, and nonlinear single variable maps, W. And typically the functions are fixed and the linear maps are learned. So a feed forward versus back propagation process. Here's a single layer. It's a function. And notice very often we have functions of just products, inner products. The forward, the x can change, but the w is fixed in the forward direction. And we get predictions. Once we have predictions, we can compare that to actual values. We can get errors, and then we can backpropagate. And backpropagation means that the x is fixed, and then we're modifying the w. Very often we call an error a loss, as we've seen earlier. And then our goal is to find weights w that minimize a loss function. And this w I have here is representing all the weights in the network as a single vector. But realize that we're looking at huge numbers of weights very often. We have a regularization term that reduces overfitting, and we have a sparsification, L1 lasso regularization. We don't always have these. Sometimes we have one or the other. It's pretty rare we have both, but that can happen. These norms are convex, and they're called regularizations. And this is the problem that we try to solve when we try to find the best weights. But it requires special software libraries. See, backpropagation means you're taking derivatives. You're using the chain rule. That means we have to use a process known as automatic differentiation. So here's a link where you can get more information about this concept, but we're going to look at some examples and just give you a flavor of what these things are about. We get what are called compute graphs. For example, suppose we have z equals the log of xy. Well, actually, we're going to say w equals log of xy, and then we get this compute graph that actually computes w as the log of the function xy. And then we're just going to let z be equal to w. That's going to add a node, but what that means is that the derivative of z with respect to w is 1, so this won't contribute to the back propagation, but it will define a backward direction that gives us the partial of z with respect to w all the way back propagated to the partial of z with respect to the x and y individually. So here's another source that you can look at about compute graphs. So backpropagation requires derivatives, which means automatic differentiation in compute graphs. It also means our functions are going to be mapping these tensor spaces to R. In other words, our feature spaces are going to be tensor spaces. And this is a vector space where you have the N1 to NP generalizes this concept of columns for P different indices, and then M1 to MQ generalizes the concept of row for Q different indices. For example, column space Rn is just the tensor space with one superscript n. Rm cross n, our grayscale image space, is just a tensor with two superscript indices, color 3 superscript indices. Matrices, on the other hand, are rows and columns, and the superscript is the vector-like columns, and the subscript is the functional-like rows. So we generalize matrix multiplication to tensor product, but you have to be careful. Tensors should be interpreted and utilized as objects in a vector space. Sometimes they correspond to matrices, but they do not define linear transformations or matrix decompositions. Tensors are vectors in a tensor space. Even the most complex data, images, video, and so on and so forth, tend to be vectors, which are tensors most of the time in some vector space. A classical vector has only one index, magnitude in only one direction, often represented by a list of numbers like a column. But a vector space is any set with operations of plus and scalar multiplication that is closed under linear combinations. So we need to think in terms of vector spaces. And a tensor is in a vector space of objects that possibly has more than one index. So these multi-indexed objects that you can combine as linear combinations, those are tensors. Very often they are interpreted to have more than one direction. So a tensor is intuitively a multi-indexed array of differentiable objects, things whose gradient can be calculated. In fact, we're going to define the concept of grad numbers. These are pairs A, B, where we interpret them as A plus B dx, where the dx squared is 0. Now, we often use epsilon instead of the dx, so therefore we're defining epsilon squared to be 0, A plus B epsilon. Notationally, if our f is A, then df is B, or df is equal to B dx. This is essentially just giving us a connection to calculus. And the grad numbers are going to form a vector space. So if I have something in the form A plus B epsilon and add it to something in the form P plus Q epsilon, well, I'll get something of the same form. So linear combinations of grad numbers are grad numbers. And we'll often use the epsilon in this interpretation also. So now we can define a product on grad numbers. Well, where did this product come from? Well, notice that if I was to take the quantity f plus df times the quantity g plus dg, I'd get FOIL fg plus dfg plus fdg plus dfdg. Now suppose that g is p plus q dx, in other words, p plus q epsilon, then df dg is bq epsilon squared, but epsilon squared is 0, so it doesn't contribute. And that means that our definition of the product of grad numbers means that we're going to end up with the product rule for calculus as the final thing in our definition. That means that grad numbers form a vector space and they have this product rule. And now we can say that tensors with the same size and the same differentiable objects, in other words, defined with the same grad number scheme, are a vector space that we call a tensor space. So here's an illuminating example. So combining tensors and this concept of automatic differentiation. Now this isn't exactly what you will find in the software, but it hopefully will give you an idea of how it all works. So here we have a matrix. K here is just some number. I could have put a 6 in here. I could have put pi. I just wanted to show a form, so this K represents a real number, which means this is a column matrix, a column in R3. It's a vector. But we want to think of it with grad numbers, and we'll need a different grad number for each position. So 2 plus dx, 3 plus dy, and k plus dz. Well, this dx, dy, and dz are going to have this epsilon in them, and we say that these things are grad numbers of order 3. Now, that means that we have this 2, 3k, and then the grad number things out to the right of that. But this is not a matrix. This is a tensor. And given that tensor, we can say square this 2, 3k. But when we square it, that's the same as squaring 2 plus dx, 3 plus dy, k plus dz. Remember, not a matrix. This is a tensor. So we're just going to square each component. And we get 4 plus 4dx plus 4dx squared, but dx squared is 0. 9 plus 6dy plus dy squared, but dy squared is 0. K squared plus 2k dz plus dz squared, but dz squared is 0. And you can see now we have this differential form. We can take derivatives just by doing calculations, and our tensors are just numerical arrays, so completely native to computers. So this is something a computer works with all the time, these kinds of arrays. In general, any smooth function from Rn to R can be redefined with grad numbers as a function from a tensor space to a tensor space, where this O here is the order of the grad numbers that we're using. So using machine learning libraries, we'll see both TensorFlow and PyTorch. We're mainly going to use PyTorch in this class. Both are based on compute graphs. They implement models similarly. The general form of implementation for both of these is you have to come up with an abstract definition of a data set. And I'll explain this in more detail later. But we don't want to use the data directly because, remember, it's going to have to be a tensor. So we want an abstract definition of the data that's fed in. We want code that's going to define a model object. It'll actually define a sequence of layers. We'll want an optimizer, and then we'll want a training loop, which keeps repeating until the expected loss is sufficiently close to 0. Now we need our optimizer for back propagation, but what do we mean by an optimizer? Well, an optimizer uses a gradient to move from a value of the weights Wn to a new value of the weights Wn plus 1 that's at a lower level in our objective hypersurface. So we want to go down and get lower and hopefully getting close to that minimum at the very bottom. Well, we want to look at this with level curves. So remember, if we add this minimum, then we can think of levels. And so what we really want to do is move down the levels till we get to the point in the middle. So here's several different levels. And I'm just going to first talk about simple gradient descent, just the simple-minded approach, most simple-minded approach. So here's W naught, that's where we start, and we have some kind of a learning rate. We calculate the gradient. The gradient is perpendicular to the tangent, and so we do the negative gradient, so it points in the direction where we're going to find the minimum. And then we take some step with a learning rate L, and then once we get to the end of that, we say that's W1. Well, Then we take another step in the gradient direction, and that's our W2, and so on and so forth. And you can see we're slowly approaching this W3, and it's hopefully will get us closer to that minimum. But there are many variations, many more sophisticated than simple gradient descent. For example, we may have a momentum term. That's where we have this mu of w times n minus 1 at the very end. And the current state of the art is actually something that has a momentum term. It's called ATM. It's the adaptive moment estimation algorithm. Because a machine learning library must be fast and efficient. So ATM is fast and efficient. Because we apply this to very large models with huge numbers of weights. And we must implement representation learning with ANNs. We may have many different layers that we have to worry about. So that takes us back to here. ANNs and representation learning, machine learning libraries will implement these kinds of systems. We'll have the first however many layers is a representation learning scheme, followed by universal approximation. The representations, where do we get those? What do we mean by that? Well, this is the past 300 years of applied math. A lot of our representation learning is based on very deep, very powerful applied math like calculus and statistics and Fourier analysis, signal processing and mechanics and wavelets, all feeding into a very modern method of approximation. So deep learning, artificial neural networks, or universal approximators, but we have 300 plus years of fantastic math and science that have revolutionized every aspect of our lives. Deep learning is where we take the 300 years of incredibly powerful math and connect them to the promise and the universal approximation schemes of ANNs. In other words, deep learning is a combination of the old and the new. But this combination requires a new type of software library. It has to be fast and efficient, and it has to calculate derivatives exactly. We want exact derivatives, no approximations, exact derivatives. And so we have to implement them using vector spaces of tensors rather than simply vector spaces in the classical sense of columns of numbers.